Greetings. Today's video will be on hypothesis statements. Hypothesis statements are a very critical part of a scientific report. It actually usually turns out to be just one sentence in the entire report, but you need to really think about your hypothesis before you start doing your research. And of course, that's going to be before you write your report. So in this video, I'll be talking quite a bit about hypothesis statements. So what is a hypothesis? Well, a hypothesis is a proposed explanation for some observations that have been made. Okay, so it's an explanation of something. Or, relatedly, it could be an educated guess, okay, why you think something is. Okay, so that could also be acting as a prediction that, if such and such, then this will happen. So a prediction about the future. So it's an explanation, a guess about the relationships between things, or prediction about what will happen. Now, something to keep in mind is that's fine for a general hypothesis, but for a scientific hypothesis, in science, we want to test things. We want to definitively find out, or as definitively as possible, find out, is it true or is it false, so that we can advance our knowledge. So a scientific hypothesis must be testable. It must be possible for there to be an experiment that could test it. So as you design a hypothesis statement for scientific research, for that type of situation, you do need to make sure that it's a hypothesis that could be tested. And if it's something that you're going to do in a classroom, for example, in a chemistry class, well, it has to be something that you could do in that chemistry class, given the type of equipment that you have available and so on. So a hypothesis is a testable statement. If it's testable, ideally it should be falsifiable. It should be theoretically possible to show that it's false, if it in fact turns out to be false. Okay? And what does it do? It predicts or gives an educated guess about the outcome. And if you're in a science class, that's probably the outcome of an experiment. Now, let me introduce some terminology. This particular video may have a lot of new terminology for you. I apologize for that, but it's important, and you'll see these terms a lot if you read a lot of science in English. In science, a hypothesis proposes a relationship. So I've already mentioned that. But it's a relationship between usually two things. It could be more than two, but ideally you should start small and simple. So between two things, two factors. What do we call these things? Well, we normally call them variables. We call them variables. So what does a good hypothesis do? A good hypothesis states a relationship between two variables. And one of them we call the independent variable. The other we call the dependent variable. I know it's very easy to get these mixed up, but you have to keep track. Some people abbreviate these as the IV and the DV. So if you see in a scientific report the IV was bum, 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 then probably they're referring to the independent variable. So the effect of the dependent variable depends on, hence dependent variable, it depends on, or it's determined by or influenced by the independent variable. So if we change the independent variable, then the dependent variable will also change. That would be a hypothesis. Okay? So let's take a look at some more information about hypothesis statements. You need to write a hypothesis statement. If you're writing a laboratory report, it's probably required, or at least your professor will be expecting, that at the end of your introduction, so before the methods, before the results, before the discussion, but the introductory section, not the beginning, usually the very last thing in your introductory section, will be a hypothesis statement. So you need to write one, and you need to write one clearly. Well, there's many ways that you can write them, of course, but a basic format would be an if-then statement. Okay, so something along the lines of, if you change this thing is what? It's a variable. Which variable is it? It's the independent variable. So if you change the independent variable, then, if-then, the dependent variable will also change, because the dependent variable depends on the independent variable. So if we do such and such, then this thing will probably occur. Okay, that's a very basic way of writing a hypothesis statement. Now, as I've already mentioned, you need to write a hypothesis in the case of science. You need to write it in a way that an experiment can be done. You could accomplish an experiment that would add support to, yes, the hypothesis is probably true. It would support the hypothesis. Or that it would show that, no, the hypothesis is wrong, it's false. And let me just mention here, don't worry about your hypotheses being right or wrong. In science, the goal is to get at the truth. It does not matter if your hypothesis is false. That's perfectly fine. That's perfectly fine. Form good hypotheses, test them, and if it turns out they're false, that's great. We now know that's not true, and we can move forward from there. So don't worry about being right. Many people want their hypothesis to be true. Don't get invested in your hypothesis being true. Write a good hypothesis, test it, and present your results. So do make sure that when you do your experiments, you'll have results that can address your hypothesis. I've seen some writing where people had a hypothesis and they did an experiment that didn't really provide strong evidence one way or the other. Now, occasionally that will happen anyway, that you'll get an unexpected intermediate result. But if the hypothesis was designed well and the experiment was designed to match the hypothesis, then the hypothesis should lead to a nice experimental design that will support or falsify the hypothesis. So make sure you're proposing testable hypotheses, things for which you can really do research, that you could really do an experiment that would support it or falsify it. Let's take a look at a few simple examples. If you drop a ball, it will fall toward the ground. Simple if then. Okay, we have a dependent variable and an independent variable, and it's very testable. It's very testable. I can get a ball and I can hold it out and I can let go and see if it drops. I can pick it up, assuming it dropped, and try again and try again. I can do this 100 times. I could do this 500 times. I could do it 1,000 times. So it's very testable. It's very clear. Okay, so this is a reasonable hypothesis in terms of forming a hypothesis. If you drop a rock and a feather, they will fall at the same rate. Maybe true, maybe false. Again, don't get tied up into it needs to be true or it needs to be false. Just what is it you want to test? What's the relationship between the variables you're interested in? Form a hypothesis that is testable. Again, this is very testable. I can hold a rock in one hand and a feather in the other, and I can let go of both at the same time and see if they drop at the same rate. If they drop too quickly and hit the floor too quickly, I can go up on a mountain and drop them off a cliff and have a friend at the bottom of the mountain to see if they hit the ground at the same time or not. I can repeat that many times. It's a testable hypothesis, so that's a good thing. Here's another example. If you increase the proportion of light exposure, so if you give more light to corn plants, they will grow faster. Okay, so we could test this. We could measure the amount of light we're giving to corn plants and see how quickly they grow. Give a different amount of light to other corn plants, see how quickly they grow. We could design an experiment to test this hypothesis that would support it or that would falsify it. For those of you that have cars, you might know that many cars come with something called cruise control. So once you're going a particular speed, you set the cruise control, and then the car by itself tries to maintain that speed for you without you controlling the accelerator. Here's a hypothesis. If you use cruise control, then your car will get better gas mileage. Many people are told this, but is it true? I've often wondered about this myself, but here's a testable hypothesis. If we have access to cars with cruise control and the time and the gasoline to do it, we could design an experiment to test this. So here's a little checklist for a good hypothesis. When you're writing a hypothesis, ask yourself, does the hypothesis relate an independent variable and a dependent variable? Okay, you should be able to identify my independent variable is this, my dependent variable is that. You should be able to clearly know what are your two variables, assuming you're doing two. But as I said earlier, try and keep yourself to two variables. If you go to three, things get very confusing very fast. Also, as I mentioned before, is your hypothesis testable? If you're going to do research on it, you need to be able to test it. You need to be able to design an experiment or design some research that will support it or falsify it. Okay? So do think about how would you go about designing your research that will get data that helps you falsify or support the hypothesis. Because if you can't test it, it may be a nice hypothesis, but so what? The point of science is to actually advance knowledge. If we can't create an experiment for it, it's probably not useful. So it's just, even though it's a good hypothesis as a statement, it doesn't help anything in science. Another thing to consider is, would your experiment, so if you think I've got a hypothesis, and yes, an experiment can be designed to test it, would it be safe? Would it be ethical? So does this involve driving a car at 300 kph on little town roads? That might not be safe, it might not be legal. So it would probably fall under not ethical and not safe. So even though you could theoretically have an experiment to test your hypothesis, you need to ask yourself, is it safe and is it ethical? Okay? And that often is not the same as is it legal, but you should probably also ask yourself, is it legal? And of course you want your hypotheses to be ones that you can design an experiment that is safe and ethical to do. One more thing you might want to do, as you should do, is once you have your hypothesis and you're sure it is testable, you do know how to do an experiment or research to support it or to falsify it, and that research would be ethical and would be safe, ask yourself, well, is there a simpler way of writing basically the same hypothesis? Sometimes people end up with these very long, convoluted hypotheses that are technically correct, but they're more complex than they need to be. Go for simplicity. Look at your hypothesis statement if it's not already very simple, and ask yourself, could you rewrite it so that it's simpler? If you can, then rewrite it, because you want a simple, clear, testable hypothesis where your research can be safe and ethical to do the testing. Now, in science, you'll often hear about something called the null hypothesis. And this is a special type or a special class of hypotheses. And in fact, in science, we almost always use a null hypothesis. If you're in one of your early science classes, depending on your professor, they may not care if you use a null hypothesis or not. You might want to check, though, because many will want you to use a null hypothesis rather than a more regular or alternate hypothesis. So what is a null hypothesis? A null hypothesis is a proposition that there is no effect between your independent and dependent variables. There's no relationship between these variables. They're not connected. So it's the hypothesis of no difference, of no effect, of no impact. And hence it's sometimes called the hypothesis of no difference. But usually we call it the null hypothesis. So there is no difference. So for example, I'm hoping you are watching these videos in order to learn how to write better. The null hypothesis would be watching these videos provides no benefits whatsoever to your writing skill. I'm hoping that if we test that, it will be falsified. Okay, but that would be a no difference hypothesis. So the null hypothesis states very clearly that there's no relationship between the independent and the dependent variables. Now, why do scientists usually prefer a null hypothesis to one that says A causes B? The null hypothesis would be A and B are unrelated. Well, the answer is that it makes it easier to do research. It makes it easier to design experiments for testing the hypothesis. Because if we have a null hypothesis and we test that hypothesis, it can be found to be false very easily. So if I say that A is not related to B, and I do research on A and B and find they are related, I can, with conviction, say the null hypothesis is false. If the null hypothesis is false, then it must be true that there is a relationship. We might not yet know what the relationship is, how strong the relationship is, if it's a causal or an indirect relationship. But if we can falsify a null hypothesis, we've proven that there is a relationship. And that allows science to move forward more quickly. So null hypotheses are generally preferred in science because we can test them, find that they're false, which actually ends up supporting the conclusion that there is a relationship between the things that we were looking at. Okay, let's take a look at a couple of examples. The rate of corn plant growth does not depend on the proportion of light exposure. So it's kind of similar to the example I gave a few slides ago, but in this case, it's written as a null hypothesis. So I can do research with corn plants, and if I find that in fact light exposure does have a relationship with how much they grow, I can say this is false. And that therefore supports the idea that light exposure does have an impact on corn plants' growth. Here's another example. Hyperactivity is unrelated to eating sugar. Many people believe that, particularly children, but some adults as well, that if they eat a lot of sugar, they get crazy, full of energy and wild, can't sleep, running around, fidgeting. Well, is this true or false? Well, we could do an experiment on this, but if our hypothesis is hyperactivity is unrelated, we have a null hypothesis. That's much easier to falsify than a regular hypothesis. So this would be the preferred hypothesis in research looking at sugar intake and hyperactivity levels. So take a look at the following examples, and I want you to ask yourself, is it a good hypothesis for scientific purposes? Consider this one. Ultraviolet light, so UV light may cause skin cancer. Is that a good hypothesis? My answer is no, it's not. It may cause it, it may not. It's very wishy-washy would be the informal way of describing it in English. It does not give a clear relationship between the two variables. We have two variables, but we do not have a clear link. It may not. It's just too iffy. It does not give a clear statement of A causing B, or A not causing B, or A being unrelated to B. So this one I don't consider to be a very good hypothesis. How about this one? UV light causes skin cancer. Think about it. Is this a good hypothesis? My answer, this is better than the first one, but it's still not really very good. So we have two variables. We have the UV light, we have skin cancer, so we've got two variables. The skin cancer is dependent on the UV light, so our independent variable is the UV light. Skin cancer is our dependent variable. But we have it, it causes it. So I'm thinking, what would my experiment be? Well, I might go to a window, open the window on a sunny day, and stick my hand outside. And then take my hand back in and look and see, do I have skin cancer? Huh, no skin cancer. This is going to be a very hard one in terms of testability. And probably, even if UV light does cause skin cancer, lots of tests will fail and show no skin cancer. So this is not a good hypothesis for science because it's not really testable, at least not easily testable. Let's try another version. If skin cancer is related to UV light, then people with a high exposure to UV light will have a higher frequency of skin cancer. How's this? Good? Or do we still have problems? Take a look, think about that. My answer, this is definitely better than the prior two. We have an if-then statement. We have independent and dependent variables. We have a relationship specified. It's very clear. And I could easily imagine designing an experiment or research that would, in fact, address this. So this is usable. I could use this. I could design research based around this hypothesis. But it's not a null hypothesis, and null hypotheses are easier to work with. So how about this fourth and final example? UV light exposure is not related to the incidence of skin cancer. That's the best of the bunch. We have two variables, independent and dependent variables. We have a clear statement, and it's written as a null hypothesis. This would be, among the four, the preferred hypothesis that a scientist would want to work with in doing research on the relationship between or the lack of relationship between UV light exposure and the occurrence of skin cancer. So when you are doing your hypothesis statement, and you should plan your hypothesis statement, you should write your hypothesis statement well before you ever design your experiments. Because if you don't have a hypothesis statement, why are you designing an experiment? The experiments or the research should test or gather data to support or refute your hypothesis. The hypothesis must come before you even design your research. So write your hypothesis statement down. Don't just do it in your head. Write it down. Make sure that it has a clear independent variable and a clear dependent variable. Make sure the relationship is clearly stated, or better yet, that it's a null hypothesis that says there's no relationship between the two. Then design your research so that it can support or falsify that hypothesis, ideally that null hypothesis. So I hope this helps you think about hypotheses and design your hypothesis statements, which would appear in your introduction, probably as the very last sentence, certainly in the last paragraph of the introduction section of your laboratory reports. So thank you for watching. I hope this helped.